Hey, chemistry, let's talk about Unit 4. Unit 4 was quite a doozy, so buckle up. In this unit, we learned scientific notation, metric conversions, moles and molar mass, how to convert to particles using Avogadro's number, percent composition, the empirical formula, and the molecular formula. Apologies to my class, we didn't actually make it to these two, but we were supposed to use them, so I am going to cover them here. Let's start with the easiest, scientific notation. Scientific notation is a simple way to display really small numbers, think many zeros after a decimal, or really big numbers. The easiest way to do that is you look at where your decimal is in a number, and you move it over to where you want it to be. Almost always, your answer will be in the form of a number, decimal, two more numbers, times 10 to the exponent. And that exponent is how many times you've moved your decimal over from the original number. So for example, if I had this number here, 7.8 billion, I would need to move my decimal over 1, 2, 3, 4, 5, 6, 7, 8, 9. And I choose to put it right there because now I can write it as 7.80 or number decimal 00 times 10, and my exponent is how many times I moved it over, which was 3, 6, 9. So times 10 to the ninth. Just note that with scientific notation, you do still need to include your units. If your number is very big, so like 7.8 billion, you do need a positive exponent. If it's really small, like this next one, you're going to use a negative exponent to indicate it is a decimal. So again, I want you to write this as 3.6 times 10. So I'm going to go over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. So that is 3.6 times 10 to the minus 10 newtons. Don't worry too much about the units for now. Just know you have to include them. From there, we learned how to convert in the metric system. Right now, there are only 3 ways that you need to remember how to convert. That is going between liters and milliliters, meters and centimeters, and kilograms and grams. Their conversions are written right here. An example of how these questions could be asked, generally we won't give you a question like this, but if you needed to convert from one form to another, you're going to use this process. So for example, if you needed to know how many grams there were in 27 kilograms, we're trying to go from kilograms to grams. Well, according to our conversion right here, we know that 1 kilogram is worth 1,000 grams. So imagine I had 20 little coins here, and each coin was worth a kilogram. Sorry, 27 little coins here. So 3, 6, 9, 12, 15, 18, 21, 24, and 27. So let's say each one of these coins represented 1 kilogram. Well, each one of these coins is also equal to 1,000 grams. So instead of counting up to 27, I would go 1,000, 2,000, 3,000, 4,000, 5,000, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 27,000 grams. That works when you have a nice small number like 27 kilograms, but what if I told you you had 2.2 kilograms? Clearly, drawing circles is not going to work. Instead, this is where we use what I call in my class the train tracks method. Mr. Barone may have another name for it, but it's how we convert. The way we convert is we're going to write how we start. So we start with, actually, let me go ahead and erase this. We're going to go ahead and start with our 27 grams. Oh no. This will not be as easy as I was hoping it would be. I can work with that. Perhaps we start with our 27 kilograms all the way on the left side. So I'm going to write 27 kilograms. I know I want to get to grams. And in order to do that, I need to divide out my kilograms. This is where a little bit of algebra or fractions are going to come in handy. Remembering that 3 divided by 3 would give you 1. 5 divided by 5 would give you 1. X divided by X would give you 1. The same thing is true with our units. Okay, this is where the idea of canceling out comes from. So if I have kilograms on the top, I just need to divide by kilograms on the bottom to get them to cancel out or become 1. Well, in order for us to maintain the fraction, I need to be sure that whatever I put over here on the top and bottom are equivalent. and that's where the conversion comes in handy. I know that 1 kilogram is equivalent to 1,000 grams, so I can write that without breaking any sort of math laws. At this point, I'm just going to multiply across the top and the bottom. So 27 times 1,000 is 27,000. My kilograms have already divided out, so I'm left with grams up top. 1 times 1 on the bottom is just 1. And because kilograms divided out, I don't have to write it. And then to simplify it, I don't need to put 1 in the denominator, so I would just write 27,000 grams. So you're probably thinking, why don't I just take the number and multiply it by 1,000? Well, that's fine if you're just going to do a simple one-step conversion. But if I were to give you a problem that was a little bit more tricky, such as 1 kilogram is equal to 2.2 pounds and you weigh 128 pounds, and you wanted to know your weight or your mass in kilograms, well, we're going to put what we start with on the left side, and we start with 128 pounds. There's no units or numbers in our denominator. And now I know that I need to divide out pounds and leave myself with kilograms. I'm trying to get to kilograms. So in order to divide out pounds, I already have it on the top, so I need to put it on the bottom here. And then I need to make this fraction equivalent. Well, according to our problem here, 2.2 pounds is equivalent to 1 kilogram. Now I can multiply across the top. That's 128 kilograms over 1 times 2.2. And at this point, I'm going to need to go ahead and grab a calculator because I can't do this one in my head. So 128 divided by 2.2 would give us 58.18. And that is how we are going to solve these. So 58.18 kilograms is the same thing as 128 pounds. After that, we learned how to convert to molar mass using our periodic table. Remember, 1 mole is the same thing as 6.02 times 10 to the 23rd particles, which is Avogadro's number, the scientist that discovered or that hypothesized that many molecules. Now, one thing that will come in handy when you're doing this for sure is a periodic table. So I'm going to quickly grab one, because the periodic table already tells us the molar mass of just about every particle. So for example, let's say we were going to do a long problem like this, the molar mass of ammonium sulfate. So in order to do that, I'm going to need to list out how many of each chemicals I have. So I have 2 nitrogens, I have 8 hydrogens because I have 2 H4s, I have 1 sulfur, and I have 3 oxygens. Now I need to go look up their molar mass in the periodic table. So nitrogen has a molar mass of 14.007. So this tells us the mass in grams of 1 mole of that element. So 1 mole of nitrogen has a mass of 14.007 grams. And then I'm going to go quickly here. 1 hydrogen has 1.008 grams per mole. Sorry for the recording. Sulfur has 32.06 grams. And oxygen has 15.999 grams. And so we can go ahead now. That would be if I had 1 of each, but I need to account for the fact that there's 2 nitrogens, 8 hydrogens, 1 sulfur, and 3 oxygens. So I'm going to plug all of these into my calculator. That would give me 28.014 grams, 8.064 grams, 32.06 grams, and I can't do that one in my, actually, yes, I can. So it'd be 16, 32, 48, so 47.997 grams. So that tells me the molar mass of each of them individually. Now I need to add them all up to get my total molar mass, and I'm going to turn to my calculator for this one. So 28.014 plus 8.064 plus 32.06 plus 47.997. And you're more than welcome to check my work here. I am moving pretty quickly, so there's a good to great chance I made a mistake. If I didn't, however, you would get a total molar mass of 116.135 grams, which tells us that if we had 1 mole of this compound, it would have a mass of this much. If I were to take 1 mole of ammonium sulfate and put it on a scale, the scale would read 116.135 grams. If I had less than that mass, I did not have a full mole. If I had more than that mass, I had more than 1 mole. Then we learned how to convert between moles and 3 different other things. So we just talked about how to go from the mole to the molar mass. We also learned in class how to go from mole to the particles using 6.02 times 10 to the 23rd. And we learned how to go from the mole to a volume of gas at standard temperature and pressure. Remember, the key there is that STP. And we know that if I had 1 mole of gas at standard temperature and pressure, it would fill up 22.4 liters. So imagine 11 2-liter bottles just to make 1 mole of gas at standard temperature and pressure. So that means almost always in a problem like this, you're going to start from 1 point on this little diagram and you're going to end at another point. So in this first problem, we want to find the mass of 0.159 moles of silicon oxide. So we are starting with moles and we want to go to mass. So we know that we have 0.159 moles. We want to get to mass, which is grams. And so in order to do this, I need to know how many grams there are in 1 mole of silicon oxide. So I'm going to go through the exact same process I did in the previous problem, only I'm going to speed it up. 1 silicon, 2 oxygen, and I'm going to round here. So this would be 16 times 2 for 32 grams. And silicon has a molar mass of about 28. And again, I'm rounding here for the sake of speed. Add them up, and that gives me a grand total of 60 grams per 1 mole. Well, I don't have a full mole. I only have 0.159 moles, so I should expect my final answer to be much less than 60. Again, moles are on the top and bottom. They divide out. I multiply across the top, multiply across the bottom, and I'm left with grams. So across the top is 0.159 times 60, 9.54 grams over 1. Alternatively, let's say you needed to find the amount of atoms based on the number of moles. These ones are nice and easy. You don't have to use the periodic table. We start with 0.58 moles. I need to divide out moles, and I want to know the number of atoms I have. Well, atoms I can figure out just by using Avogadro's number. We know that in 1 mole, there are 6.02 times 10 to the 23rd atoms. It's a ton of atoms, okay? Again, moles divide out, multiply across the top, multiply across the bottom. So that's 0.58 times 6.02 times 10 to the 23rd for a grand total of 3.492 times 10 to the 23rd atoms. In case you're wondering about rounding, read the problem for how many decimals you need to include. Now, one thing I am not showing you an example of is if you needed to go from, say, mass to volume or from volume to particles. That would require 2 steps. You would need to first convert to moles and then convert to wherever you were going from there. I encourage you to go back and look at your notes from Unit 4 to look at those practice problems. You should see several of those. Next, we need to talk about mass percent. This is telling us if I wanted to know I have a compound, I wanted to know the percent of just one of the elements in that, how could I figure it out? Well, we're going to be using our molar masses, just like we already learned, and I'm going to take the mass of that one element divided by the total mass, and then multiply it by 100 to turn it into a percent. Simple example. Let's take a look at CH4. So if I want to find the mass percent of carbon in this, I need to take the mass of carbon divided by the mass of the whole thing, which would be CH4. Well, the mass of carbon I can look up in my periodic table. It's about 12 grams. The mass of CH4 is going to be the mass of carbon, which is 12, plus the mass of hydrogen, which is about 1, except there's 4 of them, so I need to multiply it by 4. So that's 12 grams divided by 16 grams, which gives me a mass of, or a mass per, it gives me a decimal of 0.75. And then just like it shows, our last step would be to multiply it by 100. So that's the same thing as 75% carbon. Let's say I want to find now the mass percent of H4. Here's H4. So I need to do the mass of H4 divided by the mass of CH4. Well, I already know the mass of CH4, that's 16 grams. The mass of H4, well, one hydrogen is 1 times 4, so that's 4 grams. And that gives me 0.25 or 25%. You can always check and see if you did this right, because if you add up your percents should add up to 100%, which 75 and 25 do. I'm not going to show us this next example. The process would be exactly the same. It would just be much longer because now you have more elements. Lastly, we need to talk about empirical and molecular formulas. So an empirical formula is the simplest form of a formula. It basically is what's called the lowest possible mole ratio. Okay. So for example, if I had a family of compounds such as H2O, H4O, H4O2, H6O3. These are all real compounds. H2O would be what we call the empirical formula. And the reason for that is to get from H2O to H4O2, notice I just multiplied everything by 2. And then to get to H6O3, I had multiplied the original times 3. So this is the simplest way I can write the other two formulas. There are 2 hydrogens for every 1 oxygen. Determining them is a little bit more challenging. Sometimes you'll start with grams and you'll need to go to the empirical formula. Sometimes you'll need to go from percents to determine the empirical formula. I'm just going to show one example here, and then I encourage you to look back at your notes for the rest. To find the empirical formula, we need to determine the mass of each element. We need to convert the mass into the moles, and then we need to find the mole ratios. So let's do that now. We see that we have titanium and oxygen. There's 5.99 grams of titanium and 4.01 grams of oxygen. So let's take the mass of each element and turn it into the number of moles. So I have 5.99 grams of titanium. I need to turn it into moles, which means I need to know how many grams there are in 1 mole of titanium. I'm going to go to my periodic table for this. Titanium, it is right here, so 47.867. So 47.867 grams of titanium cancel out, and so I'm just going to multiply across the top. So that's 5.99 times 1 moles over multiply across the bottom, 47.867. And then I divide, which is 5.99 divided by 47.867. So this tells me that if I only have 5.99 grams of titanium, I only have 0.125 moles of titanium. Now I need to go through the exact same process for oxygen. So I know that in my compound, I have 4.01 grams of oxygen. And I need to convert this into moles. So I need to look up its molar mass. 1 mole of oxygen is about 16 grams. So again, I'm going to multiply across the top and bottom. Grams of oxygen cancel out. I've got 4.01 moles on the top, 16 on the bottom. And that tells me I have, this should be about 0.25. Yep, so 0.25 moles of oxygen. So that takes care of steps 1 and 2. Now we're going to take the lowest amount. So we have less titanium than oxygen, and we're going to divide them both by that number. You'll know you did this right because this should always give you 1. So this would be 1 mole of titanium. I'm going to divide this by the same number. And 0.25 divided by 0.125 would equal 2 moles. And so what this tells me is that for every 1 mole of titanium, there are 2 moles of oxygen, or the easier way to write this would be Ti 1 mole, O2 2 moles of oxygen. So that's all we are doing here. Lastly, molecular formula. You're going to go through all the steps we just did to get the empirical formula. And then we need to use the molar mass of the compound divided by the molar mass of the empirical formula. There are a huge number of steps to this problem, so I'm just going to show the answer and walk us through it rather than going through it all myself. First thing, we are told that vitamin C has 40.91% carbon, 4.587% hydrogen, and the remaining is oxygen. So step 1, we need to know how much oxygen we have. Well, this is out of 100%, so we do 100 minus the carbon minus the hydrogen, and so we know that we have about 54.5% oxygen. Next, we want to turn our percent into grams. The easiest way to do this is to just say, hey, let's pretend I have 100 grams so that I can take my percents and multiply it by 100. So you'll see 40.91% became 40.91 grams. 4.587% became 4.587 grams, and so on. From there, we go through the empirical formula process, which we just did. So convert grams of carbon into moles, convert grams of hydrogen into moles, convert grams of oxygen into moles. Then we take the lowest amount, which in this case is 3.406, and divide it on all of them, which is what we just did in the last problem. So we see we get 1 mole of carbon and 1 mole of oxygen, but 1.33 moles of hydrogen. So the easiest way to do this is to then multiply it so you can find a whole number. So if you take 1.33, you can multiply it by 3, which gives you about 4. But whatever you do to one, you have to do to all of them. So this tells us there's 3 moles of carbon, 4 moles of hydrogen, and 3 moles of oxygen. We can get back to the original by dividing all these numbers by 3, but our goal is to not have decimals. So again, this is exactly what we did last time. We have our empirical formula. Well, now, in order to get our molecular formula, we need to take that molar mass of the compound divided by the molar mass of the empirical formula. So let's go back. And so again, we convert our C3 into grams. So there's C3, H4 converted into grams, O3 converted into grams. Get our total. This tells us the molar mass of our empirical formula. Then we take the molar mass of the actual compound divided by the molar mass of the empirical formula. And it tells us that we need to multiply everything times 2. So C3H4O3 now becomes C6H8O6. That was really fast. You may need to watch this a few times. Honestly, there's a good to great chance that a problem very similar to this will show up. And unfortunately, we only had at most 1 or 2 days to go over it. So I would encourage you to watch this section of the video maybe 3, 4, or 5 times until you really feel like you get it. Nail down a few practice problems and you'll ace this common assessment. Thank you guys, and stay tuned for tomorrow with Unit 5.